So the recorder is up. So I'm gonna go ahead and get started with this class. Remember last time, I couldn't find my own notes on flip-flops, okay? And as it turns out, I did not title the module correctly, and that's why I couldn't find it, because it had no flip-flop on the title itself. So anyway, I found it, and it is now in control units. This is where we are currently in, is control units. The control unit is inside your processor, it's inside the CPU. That's the old term to refer to a processor. CPU stands for Central Processing Unit. Okay, that's what it stands for, CPU. These days, we do not usually use the term CPU anymore. We just call it the processor. So anyway, inside the processor, we have a control unit, which is kind of like the coordinator of everything. Okay, so what we'll do at this point is we have talked about memory, and we have talked about adders and subtractors. Okay, those things are those adders and subtractors are for doing calculations, and memory obviously is just for storing data and also instructions. We learned that because of the von Neumann architecture or the von Neumann architecture. So now we want to kind of move on and talk about a control unit, which is basically say, okay, so how do we tie all of these things together? We want to execute add instructions. So how do we execute an instruction? And in the execution of an instruction, how does it know where to get the numbers to be added, perform the addition, and then how does it know where to store the result after the addition? Okay, so we're basically designing a processor, with this part of the class. It sounds really kind of complicated, but if you look at it from the one piece, piecewise, it's not really that complicated. Okay, so we'll start with one of the most basic units in a processor, which is some people call it a register, but I can break it up. I can break up a register into the smallest unit, which is called a flip-flop. Okay, so that's what this reading material is. Now, when you look at this, you see a piece of paper with a check on it. It means it is quote unquote a quiz. But once again, this is a reading material, which basically means the quiz does not really matter. Okay, if you answer everything wrong, it's not going to impact your actual grade at all. Okay, it's not going to be graded. It's not going to be counted to your final grade. So you can just go ahead and just read it. If you want to answer some of the questions, just to double check and make sure that you understand the material, that's probably best. If you decide I don't want to answer any questions, that's okay too, okay, because it's not counted to your grade. So what I'm going to do today is to read this note out. Yep.
Can you take that little quiz as many times as you want?
Yes, I believe so. I think it is set up so they can take it as many times as you want. Let me just double check. Okay, I'm going to the settings and going to grade.
Yeah, unlimited.
Nope, I guess timing. Let's see.
No, it said it under grade. It was right there.
Oh, unlimited. Yeah, so you can take it as many times as you want. And that's the idea. The idea is, for people to, basically, okay, after you take it, you didn't get a full score, you can take it again. Okay. But I'm going to go over the material today. I'm not going to answer the questions, so I'll leave the questions unanswered. So this way, you still get to do it by yourselves. Okay, so we'll start with this part here. The most basic gates do not, I'm just reading out the first paragraph, do not have any memory. So what that means is they cannot retain the state at all. As soon as the input changes state, the output is going to change. It's just like your adder or your subtractor, okay? The moment you change the input pins to your adder or your subtractor, okay, the output pins will change their state immediately. There's no such thing as memory cannot retain any information, which is actually very important, okay? Because it doesn't really, it's not useful if you can just do calculations when you have no means to store the result of the calculations, okay? So this is the starting point of, okay, but how do we keep track of things? How does memory work inside the computer? So logically, for each bit to be stored this way, okay, which means maintaining the state of something, there has to be two inputs. So logically, if you think about it, one input is going to indicate the new state, and then the other input pin to indicate that the unit needs to be updated. So there are 2 bits or 2 inputs to a memory device where one would say, okay, let's change, and then the other one would say, okay, how do you want to change? Either that, or you can also have a circuit where you can have a set versus a reset circuit. So what we'll do is we'll work with the set reset flip latch first. So this is, I'm already jumping down here. It's called the SR latch, okay? S stands for set, which means you're turning on something. Reset is the opposite, you're turning off something. It's called a SR latch, okay? A latch is not a flip-flop, okay? But it is the smallest unit of memory, okay? It has some properties of memory, but not everything that we want to do with memory. So we'll take a look at this circuit here and go like, okay, that looks not very exciting. That doesn't look very exciting. It's made out of 2 NAND 2 gates, and it has 2 outputs and 2 inputs. So what is it going to do? Now I will do this in Logic Sim a little bit later on, but we want to kind of just logically analyze the circuit first to find out what is going to happen when I make this a 1? What happens when I turn it into a 0, and so on, okay? So the only thing, or the one thing that makes this circuit very different from all the other circuits that you have done up to this point is there's a feedback. The output of each gate is going back to the input of the other gate, not to itself, but to the other one. So you can see it is also symmetric. When you look at these 2 NAND gates or NAND 2 gates, they are symmetric. The first one takes the input out of one of the input pins, but the other input comes from the output of the other gate. But when you look at it the other way around, it is exactly the same. In other words, you can flip the design upside down, and it looks exactly the same. It is symmetric. So the question now is, okay, but what does it do? Okay, what is the thing about a NAND 2 gate? Okay, or what about a conjunction? Okay, with conjunction, there are 3 configuration of inputs where it would maintain the same output, and there's only one input that would change the output. So let's go and take a closer look at the truth table of a NAND 2 gate again, because that is important. Okay, so we just want to make sure that we understand or remember what a NAND 2 gate does in terms of in truth table. So it has 2 inputs. We'll just call the inputs X and Y, and then we have the NAND. Well, let's start with AND first, and then we will deal with the NAND, which is the negated AND. So as usual, we have 0, 0, 1, 1 for one of the inputs, and then we have 0, 1, 1 for the other input. And the regular conjunction should be no problem, right? 0, 0, 0, 1, because the only time you get a non-zero is when you have both inputs being 1s. But that is actually very important, okay? The NAND is really just the negation of that. So all the 0s turn into 1s, and then all the 1s turn into 0s. Okay, just like that. Are there any questions about the truth table? Okay, it's abbreviated because the AND is really X and Y, and then the NAND is X NAND Y. Okay, I didn't spell out the entire expression. But basically, it's a truth table that you have seen many, many times already. But you can also see that with NAND, the only time the output becomes a 0 is when both inputs are 1s. And for everything else, the output is a 1. Okay, well, let's see how that is useful in this particular design. So that means in order to make the first output pin, or the top output pin, in order to make that a 0, both of the inputs have to be ones. Is it making any sense? This is an input pin, it is controlled by something else, okay, something external to this circuit. So this one can be a 1. But how can we make sure that the other input to this gate is also a 1? Well, let's track it down. If this is a 1, that means the output of this gate has to be a 1. But if you want the output of this gate to be a 1, the result of the AND has to be a 0, which means at least one of the input pins has to be a 0. Okay, but now we can see that this pin, which is coming from the output of this thing, is going into this pin here, right? So that one is guaranteed not to be a 0, because we already said we want this pin to be a 1. We want the upper output pin to be a 1. Is that right?
You said you want that output pin to be a 0.
I want it to be a 0? Okay, so if we want this, if we want this to be a 0, then this would be a 0 already. So now it does not matter what this pin is. Okay, let's draw it out on a piece of paper, because I cannot remember what I just said. Without any way to help myself remember, I cannot remember whether I wanted the output to be a 1 or a 0. Okay, so let's start up. I should have fixed the permission thing as well, so let's see if that is also working. Open capture device. Yes, excellent. Okay, we were just talking a little bit earlier, how it's not getting updated. No, the permissions. Something happened to the USB hub, I think. Okay, so the recorder is recording again, and it's still not seeing the camera. The camera is hooked up to this port. Okay. Yeah, there it goes again. So I think there's some interaction going on between those two devices, which we did not observe before. Okay, try one more time. Still not seeing it. It's having a problem with the camera. Oh well. Well, we'll just use the whiteboard then. So you might need to write down some notes here regarding this part. So I'm going to duplicate the same design on in the notes. So we're going to send these two to the output pins. Take the output of one gate into the input of the opposing gate, and symmetrically do it to the other one. Okay, just like that. And then the inputs, we go into each one input to go into the input of one of the gates. So this is the basic design, and this time I'll make it even better by labeling the inputs and also the outputs. So XY's are the inputs, AB's are the outputs. All right. And the next thing we want to do, I'm just going to flip back to the notes here, so that this way I can make some references to the picture in the notes, just in case when people are just watching it, they can get some idea. All right, so now what we want to do is to make a truth table, okay? So now the first question is, okay, I want A to be a 0, okay? So let's say that we want A to be a 0. What can make that happen? Okay, so let's find out. So if I want A to be a 0, let's find out how I can configure X and Y to make that happen. The first thing I can do to make A a 0, well, there's only one configuration that can make A 0. I need X to be a 1, but I also need the other input to be a 1, which means B has to be a 1. Okay? So I have 3 things to look at here. I need X to be a 1. I need B also to be a 1. Okay, so I need B to be a 1. If I need B to be a 1, then at least one of the inputs to the lower NAND gate has to be a 0. They can both be zeros, but at least one has to be a 0. So don't we know at least one is already a 0?
Yes.
Because one of the inputs to the lower NAND gate comes from A. So that means one of the input is guaranteed to be a 0 already, which also means I don't really need to know what Y is. Y can be whatever. Okay? So I can, so there are different ways to specify I don't care. Okay? I can just put a question mark here to basically say regardless of what Y is, as long as X is a 1, then I guarantee A to be a 0, but I also guarantee B to be a 1. Yep.
Sir, could you please repeat that? So why is it not 1 when you go through A? Why did you make that as 0?
I want A to be 0.
Okay, that's your
So the question is, how do I make A 0? And the answer is, if I want A to be a 0, I just have to make sure that X is a 1, but then I don't really need to know what Y is. Right.
From the, I'm sorry.
Yeah, go ahead.
From the book, this is the SR latch, right?
This is for the SR latch, yeah. So which is also on the projector. Yep. Mm-hmm.
That's a NAND. Both of those are NAND gates, right?
Yes, these are NAND gates.
So if a Y is 1 and the input to the other input is also 1, won't that be a 0?
Well, when they're both 1s, there are some states that are kind of like, well, we don't know what it's going to do. Okay. So we'll just take a look at, from the perspective of A, from one of the outputs, how do we change that first, okay? So the opposing question is, what if I want A to be a 1? What if I want the upper output pin to be a 1? Okay, so if I want this to be a 1, that means the inputs into this NAND gate has to be at least, one of them has to be a 0.
So X can be 0.
So
Will be
X,
anything and Y has to be 1.
well, one of them has to be a 0, which means if I make X a 0, that will make A 1. Okay, that part is easy. However, what about the other part? Does it do anything to B? If I make A a 1, somehow make A a 1, what is B going to be?
If Y is a 1, it'll be 0.
B is going to guaranteed to be a 0. Correct. What about the other input pin? What about this input pin Y here? Now A is already a 1, okay, because that's the state that I want. So I want A to be a 1. So there's 1, 1 coming into the NAND gate, okay? And then there's another 1. If both of those are 1s, then B is going to be a 0, okay? So that means Y has to be now, it's symmetric. The relationship between A and XY and the relationship between B and YX is actually symmetric. So we only have to analyze one half of the circuit to understand how the other half works. Is that okay? So now we can look at this and go like, it looks like, there's some kind of memory, there's some kind of memory property to this whole thing. And the memory property comes from the fact that one of the input pins can be in whatever state, and as long as one of the input pins is 0, the other one can be whatever, and I can still maintain the latch in a certain state. Is that okay? All right? No? Sort of?
Say it one more time.
Okay, so let me say it one more time. If I want A to be a 0, okay, that guarantees B to be a 1. Okay, so let me just kind of, okay, if I want A to be a 0, it automatically means B has to be a 1. Okay? But since B is guaranteed to be a 1 when A is a 0, because the output of the first or the upper NAND gate feeds into the second to the lower NAND gate. This one feeds into this, which guarantees a B to be a 0. But if one of the input is already guaranteeing B to be a 0, or to be a 1, sorry, B is guaranteed to be a 1 without looking at Y. So that means Y can be whatever it needs to be. Okay, so Y can be whatever. Y can be a 0, Y can be a 1, it doesn't really matter. Is that okay? And that's an aspect of memory, because it basically says I can maintain the state of the latch just by affirming one of the input pins to be a 0, because I need X to be a 1 in order to make that happen too, because X is important, okay? So I need X to be a 1 as well. But Y can flip. Y can do whatever it needs to. Yep.
Wait, so the difficulty I'm having is that assuming you're starting from there's nothing on the line, all the wires are. I'm not seeing how you can get either one of those.
You mean the initial state?
Yeah, the initial state. How you can get any one of those to be something if you don't have if they're dependent upon each other.
Okay. It has to settle to one of the two configurations. So when you first start up, these gates they're seeing random values as the inputs. So let's just say that the inputs are not connected to anything, and it has to settle to one of the states. So let's see what happens, when you have that particular situation. Okay. Okay. So I'm going to keep the picture here, and then I'll erase this side. Okay.
So which
Yep.
is the bit that's being stored?
The bit being stored, most people would look at A as the state that is being stored. So A is the state of the latch. Even though B is symmetric to A, most people look at A as the quote-unquote state of the latch, and B is usually ignored. Okay, B is usually ignored, but you need this pin anyway. You need the output of the NAND gate, the lower NAND gate, to be connected to the input of the upper NAND gate. So most people ignore this pin, because it's not really useful, but it is nonetheless here. X and Y are the S and the R. The one is the set and one is the reset, because when you assert one of these, it will make sure that A is a high, and when you assert the other one, it makes sure that A is a low. So that's why it's called a latch, because it locks the state based on one of the two inputs. Is that okay or not? So let's see what happens when I change the input. So this time I'm changing my perspective. Instead of looking at the output and say, okay, what can make A a 0? I look at it from the perspective of the inputs. Okay, so we look at X here. Okay, so I will start a sequence of events here. So I want to make X a 0. Okay, this is the actual change of state. Okay, so you can see it's not equality, which is not asserting whether the state is a 0 or not. I'm changing it to 0. Okay, so when X is changed to 0, what is the next thing it's going to do? Well, X only goes into the top NAND 2 gate, which means the top NAND 2 gate is going to see a 0. Okay, and the output of the NAND 2 gate is the output to A, but it also has a different input from the other gate. So if I just change X to 0, it doesn't necessarily cause any actual changes to the output pins. think might have happened a few times already. Okay, so when you have 1, 1 as the input, it simply means no state change, okay? Because this is a really odd state when you have both your outputs to be 1 to begin with. That's an unusual state for SR latch. But if you do have 1, then it would just use the raise condition to determine who becomes the 0 first. And once you determine who's the winner, it keeps that state, okay? The earlier confusion that I had that thinking that it would flip-flop was because I forgot that this is a NAND 2 gate. Instead, I thought it was an AND gate where the output would be flipping, and then that's why I confused myself. The more important ones are these two. These two rows are even more important because it basically says if you have 1 is 1 and the other one is a 0 as the input, it will guarantee the output to be a 0 and a 1. In this case, if A is a 1, it guarantees X to be a 0, it guarantees Y to be a 1. And then with this one here, it is the exact opposite because the design itself is symmetric. This is the only one that really doesn't make sense and really should not happen when you design the circuit, is when both inputs are zeros. That one really does not make sense. So now it's time to relabel the pins, use the SR notation. So to use the SR notation, we basically relabel these pins, and I think there might be a picture down here, maybe not. Okay, so if there's no picture, that's okay. I'm just going to label these pins up here, and I'll use the red color to label the pins, using the terminology. This pin is called a /S. The slash once again means what? Negation, right? Okay, because when you type on the keyboard, it's really hard to do the overbar. So a slash really means negation. So /S means it is an active low signal to set the latch. It's active low, which means when there's a low, you are actually saying, yes, do it. Okay? So the other one is a /R, which is basically a negated, it is an active low signal to reset the state of the SR latch. So now we have to pick one of the outputs to be the actual state of the SR latch. And we pick A usually to reflect the quote-unquote state of the SR latch. And it has a particular term, we call it Q in electrical engineering. Don't ask me why, but we use the letter Q to denote the output of the SR latch. So the other one is basically /Q because most of the time it is guaranteed to be the opposite of Q. The only time that is not the case is when X and Y are both zeros as inputs. Yep.
Not that, it's just kind of semantics. The book you got us reading has the top being Q prime, which
okay.
I assume is the same thing as Q /, right?
Negated.
Yeah.
Yep.
So, and that doesn't matter which one we call Q prime?
It doesn't really matter.
Okay.
Yep. But then they probably have to flip the input as well.
They don't have any slash on the S and R.
They don't have the slash on the SRs?
No.
Okay.
So when you first turn your computer,
Oh no, they both are. Yeah, they're both prime.
Okay.
when you first turn on the computer, how does it set the SR latch to its initial states? Like how do you set A and B to whatever you want it to be in the initial
Well, the input pins are connecting to something else, so it depends on how you control those input pins when you first power up a computer. So that's an interesting question. It's a general question. Is when you first start up a computer, what is happening inside the computer so that it starts with quote unquote a known state, right? So most of the things will start with a 0, which means in the circuit coming into an SR latch, something from the outside would guarantee the reset to be asserted first, to basically clear the state of the SR latch. Okay? But that's a very good question because there is a system-wide reset pin or clear pin that goes to every single component in your computer that matters. And the reset pin actually stays asserted for a pretty long time because various devices take different types of time to reset itself. So it would actually a computer would assert the reset line for at least 50 to 100 milliseconds when you first turn it on.
Probably oversimplification, but is that all during like the
power up
reset?
Yep.
Yeah.
Yep. And the same circuitry usually is responsible for brownout detection. So when the supply voltage goes below a certain point, which is called a brownout because it's not a blackout. It's not dropping out to 0 completely. But when it drops below a healthy voltage, it will assert the reset line and just say, okay, don't do anything because we're passing out, but not quite passed out yet. So are there any questions about this whole thing? Yep.
Smart people.
So you said for this, the A and the B and the X and the Y are wrong. So like under A should be X and under B should be Y and under X should be
Right. This picture has the labels, just.
Which ones are the right? Am I right for that? Then so.
Well, the A, B, X, Y are arbitrary, so it only has to be consistent with the description itself. It's just that during the live demonstration, I use X, Y as the input pins, but in the notes I use A, B as the input pins.
Oh.
So that labeling is arbitrary. I just arbitrarily chose A, B, and X, Y in that case. However, when we get to the later part, to use /R or the negation of S and the negation of R, that part is not arbitrary, because that part actually has to do with how do we change the state of the SR latch. Are we still doing okay so far with this picture? Okay. So where's the memory aspect of this whole thing? I mean, why do we call this a smallest unit of memory, or at least a component to make the smallest unit of memory? What makes it, quote unquote, memorize the state?
It stays in a steady state.
It stays in the steady state regardless of the input when both inputs are ones. That is why it's called a memory module, or the smallest memory module is when both inputs are ones, then whatever state the latch is in, it maintains that particular state. And you might say, well, that's not particularly useful because we need both inputs to be ones. Yep.
But aren't they negated going in, so in a way they're both 0?
This is just a label. The slash for the input pins is really a label to indicate that when that pin goes low, we are setting the output of the SR latch. So this slash here is really just for notation purposes, because without a slash, we usually have the understanding of when the signal is high, you are doing whatever the label does. But when we put a slash in front of it, it means it's an active low signal, which means when the voltage is low, we mean to do it. Okay, it's kind of odd where a lot of input pins of the processor and the memory are actually active low. We don't see that in LogicSim because LogicSim just wants to look at the logical aspect of how components work, but not the electrical aspect of how components work. But when you work with real chips, the chip select line is usually active low, the clear pin is usually active low. So there are many pins that are actually active low, which means when the voltage is low, it is an assertion to say, yes, do it. Okay? And this pin here is no exception. It is simply saying that when the pin is low, we are setting the output to be high.
So that's telling you how to activate it.
Correct. Yep.
Is that just for like a physical properties, like setting a lower voltage is easier than trying to make a high
It has to do
voltage?
with N-channel MOSFETs. Yep. It's easier to drive a signal low than to drive it high. Okay. But the first row is why the SR latch is a latch, okay? Because once you have used one of these two rows, okay, one of these two, to set the XY pin to be a 0 or 1, when you specify 1, 1 as the input, it will just maintain the output of Q and bar Q bar. Is that okay? Because before we see this particular design, there are no logic gates that we have talked about that can just quote unquote maintain the output when the input is a certain state. When you look at the adder, when you change the output changes right away. When you look at the subtractor, exactly the same thing. This is the first time we say, oh, if both inputs are ones, we're not changing the output in any way. Yep.
So let's say we put it in a steady state. How can we later come back and grab this information?
You basically sample Q. So Q connects to the input of something else.
And then you can use that for later processing.
You can potentially feed that into another SR latch, which we'll see later.
Okay.
Yep.
So basically, in order to maintain the state in the memory, there has to be voltage going to both of them at the same time, a high.
To maintain the current state and not to change anything, X and Y, or I should say /S and /R, should both be ones. Then you're just maintaining, quote unquote, the status quo. Okay, you're not changing anything. If Q is low and Q bar is high, you're just maintaining. If it is the opposite, it's cool. You're just maintaining the current state. So this row here. Okay, I'm just going to highlight the row again. So this row is the magical part of the SR latch that makes it different from all of the other circuits that we have seen at this point. Because every other circuit that we have seen up to this point, the moment you change the input pins, the output is directly a function of the input pins. Is that okay? You change the input pins, it will change the output pin in a predictable way. Is that okay? This is the only one where you can say, okay, A, B are both inputs. What are the outputs? I don't know, because nobody told me what was the initial state. This is the first time we see something like that in this class. Does everybody understand the significance of this design? It can maintain its state when both inputs are 1. Now you might say, but that's really specific. We need both inputs to be 1s to maintain the state. How can this possibly be useful? Well, it is not that useful by itself, but we can stack other designs on top of this to make it useful. So the question here is asking, knowing only that the inputs S bar, which is /R and /R are both 1s, what is the state of Q? Okay, I just answered that question a little bit earlier. So I'll let you guys figure this one out. Okay, and on the next slide, we talk about that again. The significance of a latch is that at least one input configuration, the state of the output pin depends on the internal state of the latch and not on the input pins anymore. So that's why, but it also has a few problems. The first problem is there's no guarantee that we do not end up with both S bar and R bar being zeros. Okay, because there's nothing here to guarantee that the input to the entire SR latch cannot be both zeros, which will drive both output pins to be high, which does not make any sense. Okay, so that's one problem. The second problem is the latch changes state as soon as one of the inputs go to a 0. Okay, if you just choose one to go to 0, the other one to be a 1, it would immediately affect the output pins. Okay. In a logic circuit with other components, it is helpful to have a gated input where a single pin can determine whether a memory component can change the state or not, and we need 2 pins to control an SR latch. So just kind of focus on that particular sentence. I know it's kind of long, but let's just focus on it to find out what are the limits or limitations of an SR latch. To change the state of an SR latch, we need 2 things. We need to control both of the input pins. They should be opposing each other. Okay, so you can say, oh, we can use a negation to negate the signal. Yes, we can, but then you lose the usefulness of an SR latch. When both inputs are highs, you're maintaining the state. Is that okay? Sort of? Because ultimately what we want is to have one single pin to say, yes, go ahead and change the state, and then another pin to say, oh, let me tell you how to change the state. I want you to turn to become a 1. Okay, but we want one pin as the gatekeeper, the other pin to control the new state, to specify the new state. That's what we want. SR latch is not that. Okay, it doesn't get that done, but it's a component to get it done. Are we doing okay so far in terms of just in terms of concept-wise understanding what an SR latch can do and what it cannot do that we would like to do? Okay. All right. So now we have a new design. It's called a D flip-flop. So this is the first time we encountered the term flip-flop. And when you look at the D flip-flop, it looks like this. I'm hoping that most people see that, hey, this looks like it has, it has an SR latch built into it. Because the second half is an SR latch. The first half is not. Okay. So let's take a look at this thing here and go like, okay, what does it do? Okay, so there's a lot of verbal description down here. Okay. but instead of using the verbal description, let's just kind of play with this picture, and I'll draw it on the whiteboard, and then just play with it to see what's going to happen. And by the way, everything that we talked about today, you can do it in Logicsim, because these are all just making use of 2 input NAND gates. So everything that we do today, we can experiment using Logicsim. All right, so let's take a look at this one here. So we have D, which stands for data. Okay, so that's one input pin. It goes into one NAND gate, which feeds into, okay, so let's see. Well, I'm just thinking about whether I should use the SR latch, symbol. So I'm going to use the SR latch symbol. So we turn the second part into just an SR latch here. So this is an SR latch. And we only care about Q. We'll just toss Q bar away, because that's not really that useful. Okay. So this is our /S, which is the set pin. This is our reset pin. And the reset pin is connecting to another NAND 2 gate where data is negated to 1. And then we have a clock pin here, CLK, it stands for clock. And the clock pin goes to both gates, non-negated, like so. Okay. Put a dot here to means they're connected. This is not connected, this is just flying over. So, are we doing okay so far with the design on the whiteboard? Do you guys want me to turn on the lights on the whiteboard? Because I can't get the document camera to work, and that's why we are using the whiteboard. Do you want to turn on more lights, or is this okay? You okay? All right. Okay. All right. So we have an SR latch on that side, and then we have a data pin, and then we have a clock pin. So we want to look at 4 different configurations. Okay. Well, okay. 3 actual configurations. The first configuration is, what if the clock pin is, let's see. What if the clock pin is a 0? Okay. So the first scenario is, okay, we'll put a 0 here. Now the clock is the gate. Okay, that's the gatekeeper pin. So when the clock pin is a 0, what is going to go into what is the output of the initial of the first 2 NAND gates? They'll both be 1s, right? Because they're negating. So we don't even need to know what is data, right? When clock is 0, it guarantees this one to be a 1 and this to be a 1. When both inputs to SR latch are 1s, what is happening to the state of the SR latch? It stays the same, okay? Maintains the current state. Are we doing okay so far? Okay. So that means when clock is 0, data doesn't even come into play. It can be whatever, okay? We don't even care. Okay, fine. So we have the gatekeeper done. So now we have to make sure when the gatekeeper says go, then the data pin actually specifies the content of the new content of the SR latch. Yep, go ahead.
If data is 0 though, then the top is 1 and the bottom is 0.
Correct. Which is fine.
That's fine.
Okay, so let's see what's going to happen when clock is 1 and data is 0. Okay. So when clock is 1, that means both of these turn into just negations for the other pin. So that means D is going to be a 1 over here, and because D is negated before we get into the second NAND gate, so it becomes a 1, 1 and 1 is 1, and then the output becomes a 0. So what is that going to do to the output of the latch? We will force a state change, right? If it's not in that state, we'll force that change. Changing the Q to what?
0.
Changing the Q to be 0. So the Q is going to go from whatever it was before to a 0 in this case, because we are resetting the SR latch. Is that making any sense? Okay. So let's go ahead and take a look at the opposing, the different situation where the data pin is a 1. What is that going to do? When the data pin is a 1 and the clock pin is a 1 also, which means the gatekeeper says, okay, we're good, we're going to do it. And then the data pin specifies, I want the SR latch to be a 1. is it gonna get the job done? Okay, that's the question. So we have both ones coming in. So for the top NAND 2 gate, the output is going to be a 0 because we have 1 and 1, which is a 1. But since this is a NAND gate, a 1 turns into a 0. Is that okay? And then for the second NAND gate, we have a negated input to begin with. So we have a 0 as one of the inputs, which guarantees the output to be a 1, right? And the behavior of an SR latch is if the slash bar pin becomes a 0, it guarantees the output to become a 1. So it will turn from whatever it was before into a 1. If it was a 1 before, there simply is no change of state. Are we doing okay so far with that picture? So by using these two NAND 2 gates in front of an SR latch, we turn the SR latch into a D flip-flop, which is very much what we want, because now we have one pin as a gatekeeper and say, should we make changes? If it's a 0, if the clock pin is a 0, it means, no, don't change anything. We want to keep the current state of the output of the SR latch. But when the clock pin turns into a 1, only at that time the D pin will specify the new state of Q that is the output of the SR latch. Yep.
So because of this gate setup, you can never have 2 zeros going into
Yeah, because
That is correct. It has to do with
negation. Yeah.
this guy here. Yep. You can have both ones going into it, which is actually a useful state, because when you have both ones feeding into the SR latch, it simply means maintain the current state. Don't do a single thing about it. And that's the majority of the time. So the majority of the time, you have clock pin being a 0 or deasserted, so that your SR latch is just keeping its current state. It's only when you need to make a change, then you want to assert the clock pin, then the data pin it will specify the new state of the SR latch. Yep.
So would you like, so since those are low asserted, meaning when the voltage is low, they assert, you would make the clock high so that if it's always getting voltage, only when it's low that we flip it. Or the opposite. So since those flip when they're low, right? You would make the clock.
You mean for the SR latch?
Yeah.
Yeah, for the SR latch, the inputs are slash, which means they are active low signals.
And then that would be an active high for the clock.
The clock is active high, correct? It's non-negated. Yep. So are we doing okay so far with the smallest unit of memory? Because this really is the smallest unit of memory. The output is always there. Okay, it's always presenting some kind of output. It's just that do you want to change it? When you do want to change it, you have to make sure the clock pin is asserted first. Then you specify what you want, how you want to change the output pin. Is that okay? All right. So I just described what this part is talking about. So the question is, a D flip-flop is sometimes called a gated SR latch. Which input serves as the gate? So once again, I'm not going to answer the question. It is kind of obvious. Okay, so we have something that is a little bit more complicated here. But let's talk about why it is necessary. Okay, so what we're talking about here is, at this point we have a D flip-flop. But this particular D flip-flop is what we call level-sensitive D flip-flop, which means as long as clock is high, if you keep changing the D pin, the output will keep changing. Are we doing okay so far with that? Mm-hmm. Okay, which is not really a good thing in terms of designing a circuit with other components, because what we want is to say, okay, the D pin now has your data, and when I make a transition of this clock, pay attention. Okay, but the rest of the time, even if the clock pin is a high, don't do anything. Okay, so we want to turn the design from level sensitive, which is basically as the level changes, the output will change, into edge sensitive, transition sensitive, which basically means sample the data pin only when the clock pin is going from 0 to 1 or 1 to 0. Okay, because those designs can share with other devices a lot better than level sensitive designs. Okay. So this part is just explaining what the current design that we have from the previous slide is a level sensitive flip-flop. It is useful, but it has limitations. If memory is to be retained, then the data input cannot change as long as the enable pin is asserted. Okay, because that's the nature of a level sensitive design. This is a limitation because the data input of a flip-flop can be shared with other components. And we'll see later on in the processor, we have a lot of things sharing quote-unquote wires. So you don't want things to be level sensitive when they don't have to be level sensitive. So this design makes it an edge sensitive design, and you can see that there's one clear D flip-flop, SR latch here. And then here we have something that looks a little bit like two individual SR latches, but they're not quite SR latches. Okay, one really is one, but the other one is not. Okay, so what we want to do is to kind of look at this design a little bit here, and then just see what's going to happen. And the explanation is already down here. Okay, so the key is what if clock is 0? What if clock changes from 0 to a 1? And during the change, what if D is a 0? What if D is a 1? Okay, so this analysis basically just gives you everything that you need to know about the behavior of the edge sensitive D flip flop. Okay, so instead of just looking at the picture and work out everything, because we have a limited amount of time at this point, I'm just going to go through this part here. Okay, so when clock is 0, not changing, just flat 0, then there's no change. Okay, the D pin has doesn't do anything to the SR latch. Is that okay? It just doesn't incur any changes in that case. When we have a clock changing from 0 to 1, so we are looking at a transition right at the moment of the transition. If D is 0 during the transition, it guarantees the output to be a 0. When D is 1, okay, so you can look at this design here. We are looking at the change of the clock pin going from 0 to 1. So when the clock pin goes from 0 to 1, and D is a 0 at a time, the claim is it's going to reset the SR latch so that the state of the SR latch will be off. Okay, and the detailed analysis is over here. Okay, because S/S clock and R are all ones, /R is a 0, which is basically making sure the SR latch is turned into a 0. Now, when S/R is a 0, R is now latched to a 1, regardless of D, due to the nature of the NAND gate. So I have a special, I label this as R because it's the negated version of /R. Do you see how this is R and this is /R? Because this pin goes through here, which is negated to become this. Okay. But the bottom line is, when you follow this logic here, the design does work. Okay, but to analyze the design, you kind of have to work out various scenarios. Like, okay, what is the current state when we have this change in the input? So that's why when you look at D equals to 0, it is easier to understand. But when you look at D being 1, then we have it's a little bit longer to analyze, because when that is the case, then you have to follow the chain of reasoning a little bit further, and there are different scenarios that you have to follow. Yep.
If you were going to try to construct a truth table for this, would we kind of use clock as the independent variable? Like, how you always have, like, when you're constructing, you have one that changes less frequently?
The truth table gets a little bit harder to write with this one, because we are no longer looking at, okay, these inputs dictate the output will become that. We are now looking at certain states where, okay, when the clock pin is a 0, the output pins do not change at all. Right? Just like with the other one, the gated design.
Yeah.
But this one has the added interesting part of when the clock pin is high, it doesn't do anything either. It's only when the clock is transitioning from 0 to 1, then stuff happens.
So, yeah, okay, so you can't really draw one because you're worried about a
Then
switch
it,
as
it
opposed to
requires a different
particular
way
state.
of representing it. Correct. Yep. So when in the analysis, we are out of time today. We are just about that time. So in the analysis, what you guys need to focus on is what happens when the clock pin changes from 0 to 1. But the previous discussion is important too, because when clock equals to 0, it will also determine certain internal states. And that is important to understand what is going to happen when the clock pin goes from 0 to 1. So we'll go ahead and analyze this design on Thursday. Okay, so on Thursday, we're going to come back to this slide here, and then make sure that we understand what is going to happen with the level-sensitive D flip-flop. And then once we are done with flip-flops, then we can talk about registers, which is basically just a whole gang of flip-flops with only one single clock line, but multiple data lines and multiple Q lines. Yep.
You said you're going to demonstrate this in Logisim? Will that be in the lab or?
Yes, we'll go ahead and go do it in the lab. So we'll go ahead and bring this to the lab and continue over there.
Man, there's some smart people out